It's not. Does that look better? All right. If you have your calculators, you'll probably want to have them just available. Which one? Whichever one is. So, oh, by the way, your final exams, I don't have them with me, and we don't hand them out because I recycle them year to year. But I'll bring them Thursday bonus, and if that doesn't work for you, just email me, and I'm happy to go through your final exam with you if you want. Okay. So, it's been a while. What did we do at the very end of the semester? So we did what are called Riemann sums, okay, to approximate the area under a curve. Sound familiar? Okay, if not, let's hope it does after today. So let's just go through the first example, and I think, yeah. Okay. Refer to region R. So region R is going to be the area that's enclosed between the graph of the function and the x-axis. Okay, so we have y equals square root of x plus 2. And we want to graph that from 0 to 4. So let's just make a quick sketch. So if we're plugging in 0, we'll go up here to 2, plug in 1, 3, plug in 4, we'll go to 4. You can plug in 3, but it'll be a decimal. I think that's enough points. Okay, so there's the graph, and what I want to look at is this region in here that's enclosed. Now, I'm not going to draw. If you draw in the rectangles, just note that the rectangles for LRAM and RRAM, right, they're going to be different, and MRAM also is going to be different than the trapezoidal approximation. So if I draw them in, I might go, just so you, kind of like a warning, I might go back and erase them and do them different for the next sum. So let's look at the first one. We're going to divide it into 4 subintervals, so that makes it pretty easy. They're each 1 in length. Okay, so each subinterval is 1 in length. So we are going to use LRAM to approximate, and it says without using a calculator program. We can use the calculator program to check. We could use the calculator to get our approximation, but I want to see the setup. That's the important part. So for LRAM, now remember, these are all rectangles. So with the rectangle approximation method, we have 3 different ways. Rectangular approximation method. And then we have left hand, right hand, and midpoint. So if we're looking at these rectangles, the base of our rectangles is equal to the length of the subinterval. And then the height is basically going to be, that's going to be the height, is going to be the y value. So that's going to be the y value at each endpoint. Now, if we're using left endpoint, we're plugging in the left endpoint. If we're using right hand approximation, we're going to plug in the right endpoint. So just kind of a quick reminder. Plug into the function. So for the height, we're actually plugging into the function to figure out where it reaches. With some of these, it's going to be really easy to tell just by looking at the graph, but sometimes it's going to be a decimal, like when we have to plug in square root of 3, you'll see. It's RRAM uses the second. And then right. So LRAM starts at 0, and we're going to end up using all the endpoints except for the 4. that make sense? Okay, so LRAM. Base times height, right? Area. Area equals base times height for these rectangles. So the base in this particular example, each base is 1. So it's going to be 1 times the height plus 1 times the height. If you want, you can factor out that 1 out in front. Or, does that make sense? It's going to be in just, I'll just write it out for the first one, and then I think you guys will be fine. So the base is 1. What's this first rectangle? We'll look at where it, the left hand, right? It's going to have a height of 2. Do you see the first rectangle has got a height of 2?
Yes.
Plus, all right, the next rectangle, so now we look at 1. By plugging in 1 to the formula, or just looking at where does 1 hit the graph?
3.
At a height of 3. And then the next one, if we plug in 2, so this is going to give us a height of square root of 2 plus 2. You can turn that into a decimal if you want right now, but I'm just going to write it out and then plug it all into my calculator at the end. So remember, to get the height, we're going back to this y equals the square root of x plus 2. So by plugging in the endpoints, this is going to give us the height. So, like if I, so notice in here, if I look at from 2 to 3, if I use the left endpoint and I plug 2 in, this doesn't come out to a nice whole number. So I just plugged it in that time to make it square root of 2 plus 2. Correct. Plus, what's the next one? Well, now we're going to plug in 3. So it's going to be root 3 plus 2. This is the setup that I would be looking for. Okay. From here, you can plug it directly into your calculator. If you wanted, you could simplify it, but I'd be fine with just plugging it in. And 3 decimals always. So what did we get? Yeah, 3 decimals. What did we get? I got
something around 12.14.
Yeah, I got 146.
Yeah, 12.146.
12? Because you get 2 here, 3 here,
Oh.
plus
Yeah.
another 2 plus another 2. So basically you should have,
Yeah.
you should have 9. If you were to combine all the whole numbers, you'd have 9 plus square root of 2 plus square root of 3.
12.416.
That's good.
Is this like the degree of the units thing?
No. I mean, you could put square units, but if it doesn't say. Oh. All right, are we okay with that one? Yes or no? Is it coming back to us a little bit? Coming back. All right, let's try RAM. So I'm just going to go in here and just erase. Yeah, what's the difference between the LRAM and RRAM? If you want to look at the shortcut, it's basically going to overlap.
Take away the first one and just add. So isn't it just 14.146? You are correct.
So it's going to be 1 times 3 plus 1 times square root of 2 plus 2 plus 1 times square root of 3 plus 2. But then we have the last one also. So basically what's different is we have this rectangle here, which has a height of 4. You see that? So this comes out to approximately 14.146. Do you need to see more in terms of the picture, or was that okay? Now the midpoint gets a little bit more difficult because it's not always going to hit on the graph at a nice point. The bases are still one length, right? 1 unit in length, because that's the subinterval. So for MRAM, it's still going to be 1 times, but now what's the height going to be? So if I go back here and I just look at the picture, I'm using 1/2 to determine my height. I'm going to use 3/2 to determine my height. I'm using 5/2 and I'm using 7/2 because those are the midpoints of each subinterval. So I'm going to plug 1/2 in, so basically it's going to hit the graph about here, and that's going to determine the height of my rectangle. And then same thing for 3/2. And same thing for 5/2 and so on. So those rectangles are going to be what? Well, if I had to write it out with that, just to show you it first, it's going to be what, square root of 1/2 plus 2, and then square root of 3/2 plus 2, square root of 5/2 plus 2, square root of 7/2 plus 2. Now we get, hopefully, 13.3. Oh, you got 3 or 4? Maybe. So it's a 4. Okay, so those were all the rectangular approximation methods. For trapezoidal rule, we now look at the subinterval. So the length of the subinterval is now equal to the height. So remember previously when we looked at the rectangles, the base was equal to the length of each subinterval. But when we look here at the same picture, it's now like we have trapezoids that are up on their sides. Does that sound familiar? So I'm going to just erase this here. That's okay, I can't erase those points. So I'm looking at these trapezoids here. Now remember,
But isn't trapezoidal rule just the average of L, RAM, and R?
yes, but I want to see the setup for each one.
Oh.
That's all. I understand. You could check your answer. If you take the average of LRAM and RRAM, that will give you trapezoidal approximation. But for practice, I want you to know how to do the setup. Now remember what we had talked about? Like if you use this as base 1 and this is base 2, where this is your height, then what happens in the next trapezoid over? Well, your base 2 gets used again, and then you have like this other base. So with trapezoidal approximation, the first base and the last base get used once, and all the ones on the inferior get used twice. Does that sound familiar? Can you kind of picture it? So the trapezoidal rule, first of all, do you want me to go back to the formula?
Yeah.
Do you want me to remind you? So it's the height over 2, because remember, what's the area of a trapezoid? It's 1/2 times the height, and then base 1 plus base 2. So here's your 1/2 times the height, or the height over 2. And then here, you're going to have y sub 0 plus 2 times y sub 1 plus 2 times y sub 2, and so on, until you get to the last one, and that one's just used once. Now remember, what are the y values? That's where it reaches on the curve. Now, when we did rectangular approximation method, that was the height, whereas with trapezoidal approximation, those are your bases. So it's your base 1 and base 2. So it's like a whole bunch of these, but the ones on the inside are used twice. Can you kind of picture that, putting them all together? Okay, so let's use the formula. The height was 1, so 1 over 2. What's the first y value? You should be able to see it. It's just 2. And then the next one is going to be 2 times 3, right? look at the graph. Right here. You can also plug into the formula. Remember, it was square root of x plus 2. So square root of 1 is 1 plus 2 is 3. What's the next one? It's going to be root 2 plus 2. And then the next one is 2 times root 3 plus 2. And then the last one gets used once, and that came out to 4. So 2 and 4 are all used once, but all the other are used twice. And then just approximate that, we get, well, which makes sense when you saw that. The left hand was 12.146 and the right hand was 13. Any questions on that? Okay, I think what I'm going to do is I'm going to leave 6 through 10 for you to do for homework. Because it's exactly like this one, just a different graph. All you need to do is show what I showed. Just show the one line for the setup and then just put the decimal approximation. Okay, I don't need to see lots of work involved. So I'm going to leave this and let's jump to 6 and 7. Okay, so a sled powered by a wound rubber band moves along a track until friction and the unwinding of the rubber band gradually slow it to a stop. Okay. The speedometer in the sled monitors its speed, which is recorded at various time intervals. So it's not equal time intervals. So those approximation methods we were using was for equal subinterval length. But from 0 to 2 seconds is a time interval of 2 seconds, but 2 to 5 is a time interval of 3 seconds. So basically what we're going to do using trapezoidal rule is it's going to be a whole bunch of trapezoids added together. Does that make sense? To find the total distance traveled. Okay, the distance traveled. So let's look at the first time interval. So the time intervals are the height. And these, or that was not, basically these are all the bases. So the first trapezoid is going to be a height of 2. So it's going to be 2 over 2. And then base 1 is 6.1 plus base 2, which is 5.6. Not 2 times any of them, because they're all, again, that trapezoidal approximation method could only be applied if the intervals were of equal length. But if they're not, you have to do them as separate trapezoids. Okay, the next height is going to be 3. So it's going to be 3 over 2. And then base 1 is 5.6. Base 2 is 4.6. Do you see the pattern now? So the next time interval is 5 to 10 seconds. So my height is 5 divided by 2, and then 4.6 plus 3.2. The next time interval is 7, so 7 over 2, and then we have 3.2 plus 1.8. Running out of room. Then we go from 17 to 20 seconds, so that's 3 over 2. 1.8 plus 0.6. And finally, the last one is 4 over 2 and 0.6 plus 0. So I'll plug that. I know it takes a little bit of time to plug that all in, but see what we get. alternate. That's what I got. And this is measured in feet. So the sled went a total distance, approximately, because we don't know what was happening at, for example, 3 seconds. So this is an approximation. But using those time intervals and the speed at each time, we can approximate that it went 68.6 feet, 68.8 feet. Now, what about the average speed? How do you figure out an average? If it went over, what was the total time interval? 24. So if we take 68.8 and we divide that by the total time interval, we get about 2.867. It would be feet per second. Okay. All right. A few more things, and then oh, you might even have some bonus today. I wasn't even planning on bonus, but you guys can stay here and work, or you have other work to work on already? You don't even know. I can go get my final. I can go get the finals. If you
As
need.
much bonus as I can.
No thanks.
This is very helpful because we don't get it all.
That's true. Some of you don't have any
Enjoy
bonus.
it and watch.
Just enjoy it. Oh, you did. Okay. Okay. So the other part of what we covered before the break was just kind of an introduction to the definite integral. So this is an integral sign. Remember we talked about it as like an elongated S, representing the sum of the area under the curve. So remember, this is like area under the curve. Now you have bounds. So normally we would have like A to B. This is your lower bound, this is your upper bound. Oh, and I just realized there's a typo here. There should be a dx. The dx goes along with the integral sign, so it just means take the derivative of what's inside.
Oh, yeah.
That-
Derivative.
Well,
How do you do it?
now we take the antiderivative. We haven't learned actual antiderivatives yet. We will learn them. They're not, it's okay, because once you know derivatives working backwards, most of it's like the same idea. It's just working backwards. It's easier now that you already know derivatives. But we are going to evaluate the integral by using area. So that's what says use area to evaluate each integral. So take this graph, okay? What does this graph look like? It's a semicircle. Did we forget that? It's a semicircle. So what's it look like? It's a semicircle with radius. What's the radius of the semicircle? 3. And notice the bounds. We only want the part. So in other words, if I were to graph this, and I only want from 0 to 3, I just want that region. What's that? Oh, no, if it had a negative sign in front, then it would be the part below the x-axis, but when it's positive, it means the semicircle above the x-axis. If it said from -3 to 3, we would want the area of the whole semicircle. But because it's from 0 to 3, we just want half of the semicircle, which would be a quarter of a circle. So it would be 1/4 of pi r squared, where r is 3. So 9 pi over 4. because of it ends up being a quarter of the
Wait, so we
circle.
don't have to do derivative, do we? We need to find derivative of anything?
Nope.
Then why is it, no.
Now, we have a way to check this on our calculators. If you recall, you could do math and then number 9.
No. What is that?
So math 9 will show up with the integral sign. So we could do 0 and then type in 3. And then we type in the square root of 9 minus x squared. And then you have to put in whatever variable, oops, not there. Right. So if you have a fancy calculator, like Lindsay's, then it would put it in the 9 pi over 4.
Wait, I need to get, is that calculator allowed on the exam?
Yeah.
I just like to get. Are you allowed to bring 2 calculators?
I believe so. What's wrong?
I get different numbers from each.
It shouldn't matter.
Really? Should it be precise? What is he doing? I know.
Yeah, but it's
One I get 0.0685 and the other gets 0.685.
I'm not so concerned about that.
Yeah, because we put the dx in there for. Okay, you forgot it, but like, I don't know why it's there.
Okay. Hold on. It's actually it does have an important role. Let me explain. When we
But then we just plug it into the area formula. We use the area formula on the circle for that. One.
yeah, just use the area of yeah, you just use the area. Correct. So I'll like the next one we're going to end up with triangles or trapezoids. Okay, let me just review. When you look at the integral signs, the dx is telling us what is our variable of integration. So it might not seem so significant now, but remember when we did implicit differentiation and we did like dx of both sides, and anytime you had something with y, we had to evaluate it differently. Or when we did related rates and we had to do dt of both sides, there's a reason for that. It's the way that we differentiated with respect to a certain variable. We haven't gotten into a lot of detail, so it's kind of hard to understand now. But like if you had a variable that wasn't x here, and I told you to take the antiderivative with respect to x, you would treat the other variables differently.
No wait, it'll make sense later.
So it'll make sense later. And those of you that had like in physics, if you had a little introduction, I'll just show you here. So like if I would take the integral of x, I would want this to be dx. If I would do the integral of y, I'd want it to say dy at the end.
Yeah.
But we'll get there. Okay. Let's look at the next one here. So what does the next graph look like? It's so it's a line, right? Graph y equals negative 2x plus 4. And we want to graph it from negative 4 to 4. I'm just gonna, just to save some time. So like here's negative 4, over here's 4. So it's gonna be something like that. Rough sketch. I didn't like put all the lines in and everything. You don't really need to so much. If you graphed it on your calculator, you might get a better view, or if you had graph paper. But what do we have? We have 2 triangles. Now, do you remember when the graph goes below the x-axis, the integral ends up being negative? So we're going to count this triangle here as a positive answer to our integral, and down here it's going to be negative. So it's positive here, negative here. Well, what's the base of this rectangle? Looks like 6. Does it go 6 over?
Yeah.
So this is 6, and what's the height? We'll just plug it in. Plug in negative 4. Should get 12, I believe.
Plug negative 4 in there.
Yeah.
You get 12.
So it's 1/2 base times height. And then this triangle has a base of what? Has a base of 2. And height of 4. And I'm just going to subtract it because it goes below the x-axis. So I'll put minus 1/2, 2 times 4. Does that make sense? We get 32.